Great, and next up we're going to have Alex Rice. Take your time getting set up. We're going to hear about how quantum circuits are really just a phase.
Good here. There we go. Yep.
All right, thank you.
Okay, hi everyone. I'm going to be presenting some work I've done with my collaborators, which I've listed below. And this is work on introducing sort of a programming language or a reduced sort of syntax, which describes pure quantum computations. So in this talk, we're really sort of focusing in on the sort of this reversible fragment of quantum computing, not really considering yet the entire picture of classical quantum stuff or measurement, but with the hopes that the ideas in this paper will build up to that, or at least will be able to like slot in to existing things. So what am I going to talk about? I split this talk roughly into 3 parts. Firstly, I want to give a recap over the sort of quantum circuit model of quantum computation that we're starting with. I didn't actually know I'd be the last talk of the whole conference when I prepared the talk, but hopefully it should be, I'm going to start from quite a low level of knowledge about quantum stuff, and I'm hoping that this will be a fairly easygoing talk for the time it is and everyone's energy levels, including my energy levels, I think. So the second part is we're going to introduce this quantum if-let primitive, which is this sort of restricted form of pattern matching. And I'm going to it will hopefully become more clear by the end of the talk, and that this should all mean something to you. And then lastly, I'll explain how that comes together to give this quantum phase language. We couldn't really think of a better name. And that uses this primitive and should hopefully convince you that all these sort of quantum circuits and quantum programs really can be built with just a phase. Right. And yeah, as a little teaser, this is what a sort of example program in our example term in our program looks like. And my hope is that by the end of the talk, it'll be fairly clear what this program is meaning. So I actually did put sort of a very basic intro to quantum, which I realize no one else has done now. But I'm going to go over it anyway, just because there are some key features that are important to note. So I'm hoping that everyone is already familiar with this idea that the state of our qubits inhabits this complex number vector space, C2, as opposed to our classical bits, which are false and true. Our false value we're going to write as this ket 0, which is sort of the standard physics terminology for having a 1 in the first component and a 0 in the second component. Our true value is this ket 1 vector, which has a 1 in the second component. But then there's also, of course, things that our quantum programs can represent that are the classical programs that don't exist on the classical side. So something that's going to come up later is this ket plus state here, which is because our qubits are inhabiting this vector space, we can scale things and we can add things together. So we can add together this ket 0 and ket 1 vector, divide by this 1 over root 2, which gets us back into this realm of unit vectors. And then, we end up with this ket plus state, and this really doesn't have any classical analogue. So this is sort of this idea of superposition, being in sort of both states at the same time. And now, what was the thing we were actually going to try to represent? Well, it's these measurement-free quantum computations, and these are going to be unitary maps. So really these unitary maps, they're linear maps which have this invertibility property, which I've written below. And so the goal of the talk is to develop a simple language which we can use to represent these linear maps. Because if we try to represent them by big matrices, as soon as we add each qubit we add will double the height and width of the matrix. So this will quickly become infeasible. So obviously, what is the, so this is the key question we're trying to answer in this talk, of what can we use like nice programming constructions to build these unitary maps. And of course, the standard way of doing this is with quantum circuits. So this is sort of, we've seen these in basically every talk talking about anything quantum in the whole conference. This is sort of the standard way of representing a quantum computation. And what happens, we write our wires top to bottom, going left to right, and arrange them top to bottom, and each wire represents a different qubit. Each of the sort of symbols that appears in the diagram represents some primitive gate, and then these gates are sort of composed in like 2 dimensions in sequence and parallel. And obviously, this structure gives us quite a lot of power. The compositional structure, as we've seen, we can, even in this session, we can tell lots of things about, we can do lots of resource analysis on these circuits just on their sort of compositional structure. But the bit I really want to focus on is this idea of these primitive gates. These are sort of just being pushed in as these black boxes. And really, the only way we know what they do is by sort of looking at a matrix for these gates. And hopefully, I'm not alone in thinking that just by looking at some big list of numbers, it's not particularly obvious what each gate is meant to do or like how it should be acting on our quantum states. Obviously, we can sit down with pen and paper and work out various identities that these gates hold and how they compute. But I at least don't think it's obvious. And I feel the reason for this is that these quantum, or maybe part of the consequence of this is that these quantum gates sit at this awkward level of abstraction. They're not particularly easy to reason about, but also they're not really what the quantum computers actually are doing. So firstly, most of our the computers we have today will take some sort of fixed limited gate set, which very well may not be the one you wrote your program in. Secondly, even if you do assume that your quantum computers are actually running gates, then they're probably doing some behind the scenes sort of more compilation afterwards. And yeah, we end up in a situation where the quantum gates we have here, they're not what the hardware's doing. They're not really good for us to reason about. So yeah, in particular, I think the quantum circuit we had on the previous slide, it's probably just by looking at that, I'd be surprised, unless someone has seen that circuit before, I'd be surprised if people knew what it did. And yeah, my claim is that these aren't great things to work with, so can we do better? And the title of the talk and the thing we're going to try and get to is that, well, we can really build these quantum gates with more basic primitives. And really the most basic primitive we can possibly think of is this phase map. So what does it do? It takes, in some ways it's the simplest unitary map. What it does is it takes any vector you hand in, and it multiplies it by some scalar. And of course, because we want our states to be unit vectors, we need our scalar to also be of sort of absolute size 1. And so we can represent it by e to the I theta, where theta is some real valued angle. And this will give us some complex number on this unit circle shown there. And so I guess you can either do some calculation yourself or just believe me that all these maps like this are unitary, so they're clearly linear, and by negating the angle, we can go back the other way to make them invertible. And in our language, we're going to represent this sort of basic building block as this term pH of theta, where theta is the angle of the rotation we're making, and the pH obviously stands for phase. And then the claim is going to be that all we need to make all our unitary operators is this phase operator and this quantum pattern matching construction that we introduce in the paper. And the sort of the bulk of the talk is going to be explaining what this pattern matching constructor does. So I want to sort of start by building up to this and thinking about, well, how are we going to sort of think of pattern matching on our on qubits? So of course, for classical data, it's quite obvious how pattern matching, or at least how this simple form of pattern matching works. We have a classical bit, it has a false and there's like 2 values it can be, and we simply split into branches of whether our input x is false or true. But you might be thinking, well, I just got told that this qubit has infinitely many uncountably infinitely many different possible values. How are we going to possibly case split? And the key here is that we're trying to define a linear map, and to define a linear map, we only need to define what our linear map does on some basis. So what we're going to do is, so we need to specify it on some basis. So what we're going to do is we've got some input x, and all we need to do is say, what happens when x is 0, or this ket 0 vector, and what happens when this x is this ket 1 vector. And if we've done this, we've actually specified what our map does to all vectors by extending by linearity. So this is like high level what we're trying to do. And now I'm going to say that we actually already know how to do one of the gates we had earlier, which is this Z gate. So let's recall what that does. It's given by this matrix here, but it's possibly easier to see what's going on by saying the Z maps this ket 0 state to itself, and it maps this ket 1 state to the negation of the ket 1 state. And so we immediately see that we've already specified what the Z gate is doing by splitting into sort of the 0 and 1 parts. So we can write it as this match, and we know we need to do something in the 0 part and something in the 1 part. So on the 0 branch, well, we need to do nothing at all. If the input's ket 0, we want to output ket 0, so we don't want to change anything. What do we want to do on the ket 1 part? Well, we want to sort of negate it, and this is exactly applying one of the phases we had in the previous slides. So in particular, this will be this phase of pi, which goes halfway around the circle and gives you a -1. And my claim is that a term that looks something like this pattern match is describing exactly the Z gate. However, you might realize that this is a bit verbose, and we haven't done anything in this ket 0 branch, and actually this turns up quite a lot that we want to do this sort of pattern match and only match on one of the branches. And so we're going to borrow a little bit of syntax from Rust, which has this if-let expression for exactly this use case, where we want to do a pattern match, but we only actually care about one of the branches. And hopefully it's pretty clear what this syntax means. We specify one of the patterns at the top, and we only specify the one branch, and it's assuming that we're doing nothing on the other branch. So with this, we can convert our Z gate into this syntax, and we get this. So if we got this input q, we can say if let q is in this ket 1 state, then we'll apply a phase. Similarly, we have this S gate and T gate, which were also on the previous slide, and these follow exactly the same pattern, just with a different angle. However, all the gates here had these diagonal matrices. So in a way, they're the sort of simplest gates we could have tried to describe. So what about a matrix that wasn't diagonal? So let's look at this X gate. So this is actually sort of a classical operation, but we can still try and describe it in our language as it's a nicely invertible linear map. So what does the X gate do? It sends 0 to 1, and it sends 1 to 0. So it looks like we're kind of stuck. We have, on our 0 branch, where we can't get from 0 to 1 with just applying one of these phases, and we can't seem to get from 1 to 0 without applying one of these phases. But what you need to remember is that I said that a linear map can be specified by defining it on a basis. I didn't say that it had to be this 0, 1 basis. Another basis of this vector space complex number squared is this plus state and this minus state, which I probably should have put on the first slide but didn't. So the plus state is, I'm not sure how visible it is, but it's this 1 over root 2, 0 plus 1, and this minus state is the same with a negative sign. And it turns out that if we apply x to both of these, well, x doesn't change the plus state, and it negates this minus state. So this is actually exactly the same situation as the Z gate, except we're now working with this plus-minus basis instead of this 0, 1 basis. And so we can represent this S gate just as this term here. And that's all the actual components we need to make our sort of quantum phase language. So our terms represent unitary maps. So we have the phase operator, we have this if-let pattern matching construction, and we also borrow the sequential composition and parallel composition from quantum circuits. And then the bit that's sort of unspecified at the moment is what these patterns P stand for. And these patterns sort of represent isometries, and you can think of these as sort of specifying some subspace. So in particular, we've got the 0, 1, plus, and minus that we've already seen. We can compose these things in parallel with the tensor product. And the last bit is that if we have some pattern, we can also sort of apply a unitary that we've already defined to that to get another pattern. So if you imagine we had sort of one of these states, we could apply some unitary and get another state and match on that state. And this is all we need. This gets us a fully universal gate set, and we can do everything that we could do with quantum circuits in a hopefully much more minimal way. And to sort of, I guess, test this, we'll return to our term here and see if people can, well, maybe it won't be immediately obvious because I've sort of written things out slightly differently, but hopefully, can I actually, yeah, I have got a mouse, okay. So if you look at this bit in the middle, it hopefully is clear that this was the same X gate we had before. So we've got this B, we're matching on this plus-minus basis and doing a phase rotation. And then this outer bit is saying, well, actually, we're only going to apply that operation if our other qubit was in state 1. So hopefully, at least to some of you, it's clear that this is the CX gate that was sort of glossed over in a previous slide. One sort of last, I guess, final thing that I wanted to sort of show off about this language is that because it's sort of so minimal, it actually allows us to do some interesting meta operations that are not necessarily obvious to do otherwise. So I think inverses is probably not too shocking, is that given any term in our language, it's meant to represent this invertible map. And we can actually define this inverse just by inducting over all the syntax. So if we've got a composition, we flip it. Similarly with the tensor product, we just apply it pointwise. As I said earlier, to invert this sort of phase operation, we negate the angle. And then the sort of interesting bit, I guess, is that we don't actually need to worry about these patterns at all. If we've got this if-let constructor, we simply need to invert the body of the if-let. And then similarly, if we are in, well, differently, and if we're in a situation where we don't actually have any of these sequential compositions in our term, we can also do this sort of more general exponentiation operation, which is going sort of far outside the realms of classical computing. But we can take any of our terms to the power of any sort of real number. So in particular, we can think about square rooting various gates, which is something that I would have found difficult to think about. But with this language, I can sort of just plug in the terms and evaluate stuff and see what happens. Which I thought this was quite neat and wanted to show off. And again, really the only sort of interesting thing is that with this if-let, we don't actually need to worry about the sort of subspace selection part at all, and we just need to move into the body of the if-let. So I kind of gave a very high-level brief summary, a brief overview of the language that we introduced in our paper. In the paper, we go kind of a lot further. We introduce quite a simple type system for. So yeah, I didn't talk about types at all for this. I just wanted to give sort of an overview of how the language actually works. We gave a full categorical semantics for our language, including sort of defining semantics for this if-let operator. And in particular, this gives us semantics in the category of Hilbert spaces and unitary maps. We further defined an evaluation to circuits. So given any of these terms, you can manipulate it until it's in a purely sort of more circuit form. So in this way, we're claiming that our language is no harder to sort of compile than circuits were. We're hoping that in practice, you could do a bit better. So instead of compiling to this one specific gate set and then transferring over to the gate set you actually wanted, you should be able to define a straight translation from this one program to the gate set you actually wanted on your computer. We also went on and proved some semantic equalities that happen on always hold between terms, and really this is something we'd like to expand more on in the future. And finally, we sort of surveyed some well-known algorithms in the sort of quantum computing space, tried to sort of work out how we would write them in our language, and sort of, yeah, I'm not going to go over any of them here, but the idea is that this language isn't just sort of I guess it is made up, but it's not completely arbitrary in that it does actually seem to represent represent well-known algorithms concisely. In the future, we'd love to think about extending this to beyond the sort of unitary setting. In particular, measurement should fit nicely as we already have this idea of sort of, these patterns should already give us an idea of how we can, like which basis we can measure over. So there should be something to do there. We'd love to expand the semantic equalities we found to sort of a full, complete equational theory. It would be really nice if the sort of equational theory you can define on these terms is somehow more workable than that which we get for quantum circuits, given that. So obviously we could pull an equational theory from quantum circuits to our terms, but it would be nice if we can do something a bit more canonical. It might be interesting to give operational semantics to what we've done. And finally, we'd love to think about possible optimizations that can be done. So typically, people run circuit optimizers they run their circuit through some circuit optimizers, and these have to like encode lots of rules about how different gates act with each other. It's very possible that in this sort of higher level of abstraction, we're able to sort of see some new optimizations, but we haven't really thought about that yet. Lastly, I'd sort of like to plug that I've written an implementation for this tool. It uses the language from the paper, which is this slightly different combinator version, but it's quite nice to play around with. You can just write the sort of term, get it passed, and evaluate it, see which unitary pops out. So I know I've sort of personally been using this to think about whenever I see some funky gate in a paper or funky composition of stuff, I can just sort of type it in and see what happens. And yeah, I think that's all I've got for today. So thank you for listening.
Thank you so much. Question?
Really interesting talk. One, you only talked about doing these controls in the Z and X basis in the talk. In the actual tool, can you do it in other bases, and particularly is the Fourier basis a possibility?
So, wait, if I go back. So using this, this sort of S.P constructor, we can definitely get to any one qubit basis. So you can start, in fact, yeah, you can start with sort of actually any of the starting basis elements, apply your one qubit gate, and get to any basis you want from that. So for example, probably the wackiest example in the paper is the Hadamard gate. And to define that, you sort of you want to rotate around this point that's sort of halfway between 0 and plus. And to do that, we apply this sort of fragment of a Y gate to 1. And so, yeah, so at least for the, at least for one qubit, you can get to any basis you want. For the Fourier basis, it's something I haven't thought about as much, but I imagine you should be able to get to the same place by, again, using this operator where S is the quantum Fourier transform, and then taking P to be whatever sort of, whatever element of that basis you wanted. Yeah, this is something this is the bit I really didn't get into in the talk, but this S.P constructor allows you to specify bases other than the 0, 1 basis and the plus minus basis. I don't know if that helps.
Yeah, neat.
Yeah, hello. Thanks for the talk. It was really interesting. Well, actually, I had basically the same question as the previous one, but it was still related on the basis, the patterns that you use there. So, I mean, okay, if I understand correctly, this allows you to express all the possible bases. Otherwise, you cannot pattern match on all the.
Yeah. So by sort of universality of this gate of the gate set you can produce, you can get from any one of these basis sets. So these basis elements give you enough to make a universal gate set, and then once you have a universal gate set, you can get from any one of these to any sort of vector in.
Right.
In the one qubit space. So
and maybe following up on this, because I was wondering if there was like a more semantical justification of this fact, but this is like it's already enough, I guess. And but what kind of semantics do you have to this? Because you mentioned categorical semantics to this language. Yeah. So do you have like some concrete models?
Yeah. So I guess the most obvious, in some way, the canonical model is the model in Hilbert spaces. So there are terms of basically as it says on the slide, the terms are actually represented as unitary maps, and these patterns are represented as isometries, and what you can do is this iflet gets, it's maybe slightly hard to see without a diagram, but you can think of it as sort of picking out, using the isometry to pick out the subspace, applying the denotation of S to that subspace, and then also applying the identity on the rest. I don't know if it might be quite hard to explain, but that's sort of at least that's the model I keep in my head. The categorical semantics is a bit more general. I'm not sure we have a really interesting example other than unitaries.
Do one more quick question?
Thank you for the talk. My question is, why would you like to offer for users to write phases directly? What is the high-level sense of manipulating phases directly?
Sorry, I didn't catch all of that. What did you say?
My question is, why would you like to offer phases directly for users? What is
I guess we at least need some base operation to get started. In a way, so we make sort of no distinction about the number of qubits we're using, so we need to at least represent all 0-qubit unitaries, and all our 0-qubit unitaries are one of these phase operations. So we must have some way of representing these operations. So yeah, we chose that as our sort of primitive to get started. The main thing we're trying to do is break down the sort of break down the primitive gates that appear in other languages, and we're sort of hoping that really you could take any other quantum programming language that currently uses gates as a black box and plug something similar to this in. I don't know if that really answered what your question was.
All right, let's thank Alex again and all of our speakers.